In this tutorial on SGEMS, I'll be covering some basic notions of Kriging and do some simple examples so that you get started with Kriging. The data set we'll be using is this complex data set from a porphyry copper deposit. We're looking at grades, which is the data here on the left-hand side. So what you notice also is that we have some kind of a geological interpretation of that, where we notice these concentric lithologies that are embedding themselves. So that has some interesting consequences. Some people, of course, may say, well, I may need to calculate a variogram per each lithology. And that is true. For example, that may be quite useful. It's also quite useful for sedimentary systems where, for example, say the variogram of the channel sands are very different from the variogram of the background shales. In this case, I will just not do that. It's just a first tutorial on Kriging. And the other thing is that we haven't mentioned yet variogram modeling in the previous tutorials. The way I like to approach that is to first talk about Kriging and then about variogram modeling. I think that gives variogram modeling a little bit more of a context. Just that you need to understand that in order to do Kriging, we do need to have some kind of a variogram model that interpolates the experimental variogram. But as you will see from the SGEMS input, is that if the variogram is quite simple, then you don't have to essentially create necessarily a model. It's just that you do need to create some kind of an interpretation in terms of parameters of what you observe in the experimental variogram, and that can then be directly translated into SGEMS. For example, imagine that we had looked at the variogram of this copper data set. I believe we looked at it in the previous tutorial on variogram calculations. And we know that the SIL here in variance is 0.285, the nugget is 0.15. Imagine that we have a horizontal range that's omnidirectional. In other words, there's horizontally we have isotropy with a range of 10, and vertically we see more continuity, and we have a range of 20. So all this, of course, is in units of grid cells of some kind of bounding box domain that captures all this information, all this grid data. Then also we have observed that at the origin, in the increase of variogram at the origin, it appears to have linear behavior. Okay, so here we notice some the same copper grades, and so if you go to this algorithm window and you select Kriging, which is what is done here, then this input shows up. So in this case, I've already created a Kriging grid. If you want to create a grid, so this you notice that I've already been trying things out. If you notice this grid here, that's a Cartesian grid, and so that has this amount of cells. So how to create a Cartesian grid is to simply go to Objects, New Cartesian Grid, and fill out the same information here. Then you will create a Cartesian grid on which we'll then perform Kriging. So imagine we have that Cartesian grid. So that's our Kriging grid, and we call the property copper grade. Let's say we do ordinary Kriging, and we need to load our data, which is then the drill hole data, copper, etc. Okay, before looking at search radius, let's look at search radius. It's easy to do here. So now what we need to define is in our Kriging system, we need to look at if I'm in a certain location. Let's make this all white here. If I'm at a certain location, I can do global Kriging, which would involve using all the data. But if you have a lot of data, that may be, first of all, that may be difficult to do. And secondly, that may also not reflect any local variations of the mean. Remember that in ordinary Kriging, the mean is removed. And so essentially by using a moving neighborhood, we are sort of reevaluating that mean within that neighborhood if we only use a limited amount of points within a neighborhood. So what you will ask, what neighborhood it is, how do we do that? That of course is also dependent on the interpretation that you make in terms of lithology. For example, you would not need to want to, for example, use data that have very different lithologies. If, for example, the variogram also has different lithologies, is very different. So that's more of a complicated issue. Here we'll just use the basic setting, and we'll just use a single search neighborhood. So how do we define a search neighborhood? Well, for that, I'll need to go back to presenting that to you with some slides. Okay, let's talk a little bit about the definition of the search neighborhood. So in SGEMS and also many geostatistical software, we'll be using that by means of in 2D an ellipse and in 3D an ellipsoid. So what it essentially means is that, let me put my pointer on, if, for example, you're at this location, you want to estimate something that's at this location, what you will be doing is only retaining data points that are within this area, and so ignoring any data points that are outside that area. And so then the question is, how do you define this ellipse? Well, in 2D, an ellipse is simply defined by setting what is called a major, knowing the major axis here, and the intermediate or the smallest axis here. And then the only thing we need to specify then is how to rotate this ellipse, and then we can sort of play around with the azimuth, these axes, and so on. So in SGEMS, this is done using the azimuth angle, which is always a rotation from north-south. So the y-axis is considered north-south, and the x-axis is considered east-west. If we are in 3D, which is of course the case here, then it gets more complicated. Then we need to define an ellipsoid, and an ellipsoid is uniquely defined by defining 3 axes lengths, so that would be A, B, C here, and 3 angles. Although I would say that there are really only 2 angles that are important. First of all, just like in 2D, we can rotate this ellipsoid along the y-axis, and that will be the azimuth rotation. And then we can dip this ellipsoid down along this new axis, in those new x prime axes, and that gives us the dip. And then we can even rotate that along another axis, which is called plunge, but that's not something that I've ever used in my practice of geostatistics. So important is therefore that in 2D you need to specify 3 parameters, which is the length of this axis, length of this axis, and then the angle at the azimuth. In 3D, usually, in most cases actually, we need to specify only 2. We have 6 parameters, but we need to specify 5, which is A, B, C, and then the dip and the azimuth. So here's then how that works in terms of the input. This is the window that we saw before in SGEMS. And what we notice here is our ellipsoid. It's oriented north-south. So there are a number of parameters here, as you notice. Let's focus first on this bit, which is where we talked in the previous slide. So the way it works is that if you want to define your ellipsoid, is that the first thing you have to define is the ellipsoid axis. So these are these lengths here. So if you're in 2D, you only need to worry about max and medium, and you can ignore min, and you just, in that case, just set mean equal to median. If you are in 3D, then you have 3 axes. So here, for example, I would take max that. If I want to now have, say, because my continuity is larger in the vertical direction for this particular case. So, for example, I'd like to search more data points in the vertical direction versus the horizontal direction. Then I'll need to dip this ellipsoid, in other words, rotate it by 90 degrees downwards, such that an ellipsoid that looks like this. And that is at 90 degree dipping. So the way it works is you first define the ellipsoid axes that are oriented north-south, and then you do your orientations, which goes azimuth or dip, and the end result is your search ellipsoid. So, okay, so now you wonder, what should my search ellipsoid be? Well, that depends on your variogram. And so it makes more sense that if you have lots of continuity in the vertical, then you would search for more data in the vertical direction. because that will then inform that particular point that is going to be estimated, or that unknown value that needs to be estimated at the location. So then you get a new set of inputs, and we notice here maybe some things you already recognize, which is there's a nugget effect. That's great. This seems funny, a spherical. What does that mean? Okay. But this seems already familiar. That is essentially how we input the variogram ranges and directions seem to be very similar as we've seen before with the search ellipsoid. So let's discuss this a little bit. Okay, so here we see that same window here, or that same input window that we see in SGEMS. And so now the question is, okay, we have our variogram interpretation. Remember, this is from our grade set, so we have some nugget effect, so some horizontal range, vertical range, etc. So you have another example of a case, and this is something we will discuss in more detail when we talk about variogram modeling. So in order to input all this information here, I'll need to look at, okay, I know, for example, in our case that the vertical is the largest direction of continuity. So as you remember, in our variogram calculation, we calculate variogram over in various directions. And so typically what we're also looking for is in which direction do I see the largest range, and in which direction do I see the smallest range. Actually, if I would calculate variogram in various directions, and this is a variogram map, that's something we'll discuss in greater detail when we look at variogram modeling. What this map essentially says is for example, these values here are basically the same values as on this y-axis. Okay, so this is the semivariance of the variogram. So I mean, in other words, this value at lag distance of 500 for this direction is equal to 8. So if I go now in this direction, which is the 105-degree direction, which would be this direction, I'll find at 500, I'll find this green value here. So you can see that if I connect all these pixels along this direction, I'll find all these dots that I notice in this direction. So I have the same in this direction. So what we then notice is that, again, we get this elliptical shape. So that means that the variation of this range seems to follow an elliptical shape. So this is the way then also we'll be defining the variogram and its anisotropy. It's called geometric anisotropy. Again, something we'll discuss in greater detail in variogram modeling. And so the way that enters is that for this particular case, we notice that we have the major range is 2500. So that will go into, this is the length of this axis. And the length of this axis needs to be defined, which is this minor range is say 1200. So that we're looking up around here, 1200. This is 2500. I'm in 2D, so this doesn't really matter. And then I need to specify this azimuth. So this is a rotation, remember, from the y-axis in SGEMS. So you rotate 105 degrees, and you have now defined this ellipse. So this ellipse essentially defined the variation of the correlation length to the ranges over various directions. Okay, what next? Let's look at the nugget. So for example, here the nugget is 3. Let's say it's 3. That's easy. We put here 3. Then from then on, I have the variance is 29. Sorry, it's 32. So the amount I've left here is 29, and that goes into this box, the contribution. Again, we'll talk a lot about this a little bit more in variogram modeling when we talk about nesting of variograms. Then the last thing we notice is that this is quite smooth at the origin. In other words, it starts slow and then it starts to increase. It's not like it's linear like we saw with our previous case. So this is in order to specify that, we basically will focus on 3 types. Again, something I'll explain more in variogram modeling is it either starts slow or it starts linear or it goes very fast, exponential. So we have exponential. The linear case is called spherical, and the slow case, the smooth case, is called Gaussian. So we put here Gaussian, and we have our variogram. Okay, so this also gives you some indication of search directions, of course. Often what I do is just either punch in the same numbers, or in some circumstance you want to possibly take some more values or some less values depending on trend and anisotropy and so on. But in terms of stationary neighborhood, this could also be a good start. Of course, in our case, this will be different, and as we'll see in the next window. Okay, so we're back here in SGEMS, and so we've input that information about our interpretation. So we have a nugget effect. Then I look at the variance, which was 0.285. I subtract the nugget effect, and I get my contribution. Our behavior was linear, so that comes down to this type is called spherical. And then here you have the information about the maximum range was 20 in the vertical direction, 10 in the horizontal direction, plus it was isotropic, so means also 10 in the horizontal would be just isotropic. This is this part. It's horizontal because I have my ellipsoid, and in order to get this maximum in the vertical, I dip my ellipsoid by 90 degrees, and then I essentially have defined my geometric anisotropy for the variogram. So in terms of the search then ellipsoid, we could just start with something. It doesn't have to be correct immediately. So I just put in the same kind of search parameters as I have for the variogram. Okay, so we're all set, and we can now start run Kriging. So as you notice, this goes actually pretty fast, so you may be very encouraged. Unfortunately, I'll have to disappoint you in a bit. There we are. That's pops up, and that's actually what I expected, probably what you didn't expect, which is that at some location the Kriging system was singular. So a lot has to do with the amount of data you take into this search neighborhood, and that has to do with this part here, which I haven't talked about yet, and something we'll mention now, and also becomes clear why this is important when we actually look at the result. So here we notice that in our Kriging grid, I have my copper grades. So I look at that, I get this not so fancy looking result. So we notice that indeed a lot of our grid is just gray, which means no number or an NEN number, and then everything else looks very patchy. I noticed that I could maybe toggle a little bit in terms of the Kriging grid and cut this down a little bit, gives you a better idea. So I get this really kind of ugly looking result. It seems like there's a fault in there, and you get these elliptical shapes. So why is that? Well, that has a lot to do with the fact that in terms of conditioning data, you notice that you can also specify a minimum amount of data to have in the search ellipsoid and a maximum amount of data to have in the search ellipsoid. And so for 3D applications, this is really way too small. In particular, the minimum, you imagine that Kriging with just 1 point is going to be a big issue. And this issue we had discussed also in the slides on Kriging, where we said that that with shifting neighborhoods, we get this kind of sort of tent-forming behavior, is that sort of the overlapping tent-forming behavior, which is due to the fact that if you have a small amount of data in your neighborhood, then one data entering or exiting your neighborhood will create a discontinuity in your Kriging estimate. And the discontinuity shows up in this form in terms of sort of these tents and faults that you appear to be there, which are absolutely not there. So a solution here is to increase either the search ellipsoid or the amount of conditioning data. Okay, so here I have changed the search ellipsoid. I noticed that I dramatically increased the number of minimum data points and also the increase of maximum data points. One sort of a cool idea that in order to avoid a lot of this circular and tenting shapes in your Kriging is that you keep the amount of data points relatively constant, so that when you shift your search radius, all of a sudden you don't go from, say, having 20 data points to only having 5 data points. And that's often causing all this discontinuous behavior. There are other methods that have been presented or developed, which is adding noise to the diagonal of the covariance matrix, etc. So in more advanced software, at least in terms of Kriging, you can find some of these things implemented. So here on the right-hand side, then we see that result, and we notice that we still have some of that kind of discontinuity that's occurring. But if I notice here that we get sort of at least a nice, relatively nice looking Kriging map, certainly compared to before, we notice, of course, the high grades in terms of the porphyry copper and the low grades that we see here in the middle. Okay, so if you keep playing around with that, you can get nice results. So here, notice some sections in both the vertical as a horizontal direction, and so we can kind of zoom in a little bit into that model, look at that, and see. Yeah, that looks nice. You see that where you have high grades in the data, you get this nice high interpolations, and it looks similar into the direction. As mentioned in the tutorial on, mentioned in the lecture on Kriging, there's a second part that you get with this, which is called the Kriging variance. So you have this copper grade. So this would be the copper grade Kriging variance. So let's look at that. So Kriging variance looks like this. As you notice, Kriging variance is simply low where you have a lot of data, and it's high where you have very little data. And so in that sense, I don't find this necessarily quite informative. It's sort of obvious that the Kriging variance, the Kriging variance is 0 at the location of the data. And so, so it's not quite, there's a nugget term, so not quite 0. But as you notice, if you have no data, then the Kriging variance is high, and it's high around the edges. So it's just a kind of an indication how dense your data is there. And that's something you can do without Kriging variance. Last thing I want to mention is that you can also do simple Kriging, which would involve entering the mean. So if you're quite certain about that mean, let's look at your grade data here. Mean is 0.66. So if you're certain about that mean, and you're also certain that it's quite constant over the domain, then you can use simple Kriging. Another type of Kriging we discussed is Universal Kriging. So in Universal Kriging, we can enter trend functions. So if I suspect that there's a trend in the x direction, then I hit here x. If I suspect there's a trend in the y, I would enter it in the vertical z. If I think there's only a vertical trend, then I would just add z. And I can have more complicated trend functions. So you can say, oh, why not tag all these boxes? Well, that often is a problem. First of all, you have to then calculate a residual variogram by fitting this entire trend components. That's, I again refer to the lecture on Kriging. And also there's a higher risk of your Kriging system becoming singular because you just don't have that amount of information there to distinguish between all these trend components.